Alright, hello everyone and welcome to our 3.10 lesson on the AP Chemistry curriculum, which is going over solubility. In this lesson, we are focusing on how intermolecular forces determine solubility. Substances dissolve when the interactions between the solute and the solvent particles are strong enough to compete with the attractions within each substance. So a key idea is like dissolves like. So polar substances tend to dissolve in polar solvents like water, while nonpolar substances dissolve in nonpolar solvents like hexanes. This explains why ionic compounds often dissolve in water and why nonpolar molecules do not. Understanding these interactions are going to allow us to predict when substances will mix, separate, or even form precipitates. Solubility is all about whether a substance can dissolve in a solvent to form a homogeneous or uniform mixture. If a solid is soluble, it's going to completely mix to form a solution, but if it's insoluble, it's going to stay in its separate phases. The key idea is that polar and ionic solutes are going to dissolve in polar solvents like water, while nonpolar solutes dissolve in nonpolar solvents like hexanes. This is where we get our rule, like dissolves like, which you will hear a lot of in this lesson. Now looking at our diagram on the bottom here, the type of intermolecular forces that are present, such as dispersion forces, dipole-dipole interactions, hydrogen bonding, or ion dipole forces, are going to determine whether a substance will mix or stay apart. So for example, if we were looking at heptane and pentane, those are two nonpolar molecules, which means the only type of intermolecular force they have are London dispersion forces. And when we take those two molecules or samples of molecules and mix them together, because they have the same intermolecular forces, there will be a dispersion force between each of those molecules. So because they have that same intermolecular force, there will be an attraction between the two, which is why heptane and pentane are soluble with each other. And that works with all of these examples. Acetone and chloroform both are polar molecules which have dipole-dipole interactions. So when we mix them together, they're going to have dipole-dipole interactions with each other, which is why they are soluble. Every solution has something called a saturation point, which is the maximum amount of solute that can dissolve in a solvent within a set of given conditions. So once this point is reached, no more solute is going to dissolve unless you change those conditions. So the saturation point is going to depend on three main factors: the temperature, which is our x-axis, the solvent, which in this case is going to be water, and the solute itself, which is going to be labeled on each of these curves depending on which one you're looking at. For most substances, the higher temperatures allow more solute to dissolve. This relationship between these three factors are known as our solubility curve, where you can see how different salts dissolve in water as the temperature changes. So let's do a few examples here just to make sure we can understand how to read this curve. At 40 degrees Celsius, the solubility of KNO3 is about 65 grams per 100 grams of water. So looking at KNO3, that is this green curve here, it says at 40 degrees Celsius, we can dissolve about 65 grams of KNO3 in 100 grams of water. Then it says what would happen if 80 grams of KNO3 is added to 100 grams of water at this same temperature. So now we have 80 grams, which is here, at the exact same temperature. So what that means is this first initial dot is our saturation point. That is the maximum amount of salt we can dissolve into water before it is fully saturated, and you can no longer dissolve any more solute at that temperature. So what happens when we add 15 grams more of KNO3 at the same temperature? Well, we're going to have a saturated solution, and then we're going to have 15 grams of solid KNO3 that's going to remain undissolved at the bottom of the container. So the maximum solubility is 65 grams. So if we're still at 40 degrees Celsius, adding more than that, it doesn't increase how much dissolves. The excess is just going to stay a solid. The next question says, at 30 degrees Celsius, the solubility of sodium chloride is about 36 grams per 100 grams of water. So sodium chloride is going to be our light blue curve here, and it says at 30 degrees Celsius, we are at, oh, wrong curve. We are at here, about 36 grams per 100 grams of water. It says if you dissolve 25 grams of NaCl in 100 grams of water at the same temperature, is the solution unsaturated, saturated, or supersaturated? So it's saying at the same temperature, what happens if we only dissolve 25? Now, it is below the sodium chloride curve, which means we can dissolve all 25 grams of that NaCl of water into water, but we can also keep dissolving more if we want to reach a fully saturated solution. So this solution would be unsaturated if we only dissolved 25 grams of sodium chloride in 100 grams of water. All right, so now let's go through different factors that affect solubility. So we already went through polarity, and that's going to follow that like dissolves like rule, where polar solutes dissolve better in polar solvents, and nonpolar solutes dissolve better in nonpolar solvents. Moving on to pressure, pressure is only going to affect gases. That's because solids and liquids have a set volume. So since pressures have a variable volume, we can manipulate the pressure and change the volume. So with a higher pressure, more gas particles are going to be forced in solution because more gas particles are striking the surface of the water because of the lowered volume, as you can see here. So there's less space for them to move around, which means they're colliding with the water more frequently, and then they can dissolve more. Whereas if you were to decrease the pressure, like in here, they're going to have more space above the water's surface to move around. They're going to strike the water less frequently, which means they're going to dissolve less into the solvent. So then moving on to temperature. Temperature is going to affect solids and gases differently. For most solids, high temperatures increase solubility because hotter solvent particles move faster and collide harder, which is going to help pry solute particles apart and surround them. But for gases, higher temperatures decrease solubility because the gas molecules gain enough energy to escape the solution, or essentially get out of the liquid and become a gaseous state in whatever environment it's in. So now let's look at the concentration of solvent. Increasing the concentration of your solvent is going to mean that there are more solvent molecules that are available to surround your solute particles and pull them apart. And that means more of our solute can dissolve into the solvent. Next, we have presence of other substances. This can change the solubility by altering the solvent's properties or by competing for interactions. For example, electrolytes in water can help by stabilizing solutes, or they can hurt it by crowding out binding sites. So adding other substances within your solution can either inhibit or accelerate your solubility. And then finally, we have surface area. That's going to matter because smaller solute particles expose more area to the solvent, and that's going to allow more collisions between the solvent and the solute particles. So the solute is going to dissolve faster and often more completely. So, for example, when we did our aluminum to alum lab, we talked a lot about the aluminum, and everyone kept asking, how small do these aluminum pieces need to be? Well, the smaller you tore them up, the faster that reaction in the potassium hydroxide happened. So if you wanted to leave them in much bigger chunks, sure, that would still work, but it's going to take longer for that KOH to dissolve that aluminum foil because it has a greater particle size and a smaller surface area. All right, pentane is a hydrocarbon with a boiling point of 23 degrees Celsius. That is the molecule on the left. Butanol is an alcohol with a boiling point of 117 degrees Celsius, which is the molecule on the right. And their structures are shown below. What is the significance of their molar masses being approximately the same? So whenever AP gives you two different molecules or more molecules, and it's telling you that the molar masses are about the same, they're trying to hint at the fact that you do not need to look at London dispersion forces, because we know London dispersion forces are going to differ depending on how big the molecule is or how many electrons it has. So if it's telling us that they're about the same size, it's giving us a hint like, okay, these London dispersion forces are going to be about the same in both of these molecules, so don't focus on that. So the answer to this question would be the significance of the molar masses being nearly the same is that the difference in boiling point cannot be attributed to London dispersion forces. Given the similar molar masses, explain the observed large difference in boiling points. So looking at pentane, pentane is all carbon to carbon bonds are carbon to hydrogen bonds, which are all nonpolar bonds. That makes pentane a nonpolar molecule. So the only type of intermolecular force pentane has is going to be your London dispersion forces. Then with butanol, butanol has a hydroxyl group on the end of it. And this hydroxyl group has a hydrogen attached to an oxygen, and it also has an oxygen with lone pairs on it, which means this molecule can partake in hydrogen bonding. So butanol is going to be a polar molecule, and it can participate in hydrogen bonding. Now, we know from our past lessons on intermolecular forces that hydrogen bonding is one of the stronger intermolecular forces. So because butanol has much stronger forces between the molecules in a sample, it's going to take a lot more energy to break them apart, which is why its boiling point is so much larger than that of pentane that only has London dispersion forces. All right, and then for our last slide of this lesson, it says one dissolves readily in water while the other does not. Based on their structures and intermolecular forces, explain which one you would expect to be soluble in water and why. So we already addressed that pentane is a nonpolar molecule and butanol is a polar molecule with hydrogen bonding. So remember the phrase that we've been using this entire video, which is like dissolves like. And because water is a polar molecule that partakes in hydrogen bonding, butanol is going to be much more soluble than pentane would be because they have the same intermolecular forces, which means they will attract to each other when they are put in the same environment. So I want to be very clear. I don't want you to ever explain a question like this using the phrase like dissolves like. You need to still explain why it happens. Like dissolves like is just a very simple phrase that we can keep telling ourselves so that we know, looking at two different samples like pentane and butanol, we know which one of those are going to dissolve in water because one of them is more polar than the other. All right, if you have any questions, please feel free to reach out. I hope this helps. Have a wonderful day. Bye.